NENOMATICA, where mathematics meets YouTube excellence. Welcome to our math lesson on algebraic expressions and their evaluation. Today, we'll learn about how algebraic expressions represent numbers that depend on the values we substitute for the variables. An algebraic expression is a mathematical statement that consists of variables, constants, and operations like addition, subtraction, multiplication, or division. For example, the expression 3x plus 5 is an algebraic expression where x is the variable and 3 and 5 are constants. The key concept to understand is that an algebraic expression represents a number whose value depends on what values we substitute for the variables. When we replace the variable with a specific value, we can calculate the value of the entire expression. We often use function notation to represent algebraic expressions. If we denote our expression as f of x, then f of a represents the value of the expression when x equals a. Let's work through an example to see how this works in practice. Consider the expression f of x equals 3x plus 5. Let's find the value of this expression when x equals 2. To calculate f of 2, we substitute x equals 2 into our expression. This gives us 3 times 2 plus 5, which equals 6 plus 5, which equals 11. So when x equals 2, the value of our expression is 11. Let's try another example with a different expression. Consider g of x equals x squared minus 4x plus 7. Let's find the value when x equals negative 3. We substitute x equals negative 3 into our expression. This gives us g of negative 3 equals negative 3 squared minus 4 times negative 3 plus 7. Now, negative 3 squared equals 9. And negative 4 times negative 3 gives us positive 12. So our expression becomes 9 plus 12 plus 7, which equals 28. Therefore, when x equals negative 3, the value of our expression is 28. Today we're going to compare two rational expressions and see if they're equal for different values of x. Let's look at our two expressions. The first expression is x plus 1 divided by x minus 1. The second expression is x squared plus x divided by x squared minus x. We'll evaluate these expressions at several values of x and compare the results. Let's start by evaluating both expressions when x equals 3. For the first expression, we substitute x equals 3 into x plus 1 divided by x minus 1. For the first expression, when we substitute x equals 3, we get 3 plus 1 in the numerator, which is 4, and 3 minus 1 in the denominator, which is 2. So the first expression equals 4 divided by 2, which gives us 2. Now for the second expression, substituting x equals 3, we get 3 squared plus 3 in the numerator. 3 squared is 9, plus 3 gives us 12. In the denominator, we have 3 squared minus 3, which is 9 minus 3, giving us 6. So we have 12 divided by 6, which simplifies to 2. So we can see that both expressions equal 2 when x equals 3. Let's check another value. Now, let's evaluate both expressions when x equals negative 5. For the first expression with x equals negative 5, we calculate negative 5 plus 1 in the numerator, which is negative 4. In the denominator, we have negative 5 minus 1, which is negative 6. So we have negative 4 divided by negative 6, which gives us 2/3. For the second expression with x equals negative 5, we have negative 5 squared plus negative 5 in the numerator. Negative 5 squared is 25 plus negative 5 gives us 20. In the denominator, we have negative 5 squared minus negative 5, which is 25 plus 5, giving us 30. So we have 20 divided by 30, which simplifies to 2/3. Again, we see that both expressions equal 2/3 when x equals negative 5. Let's try a fraction next. Let's evaluate both expressions when x equals 1/2. For the first expression with x equals 1/2, we have 1/2 plus 1 in the numerator, which is 3/2. In the denominator, we have 1/2 minus 1, which is negative 1/2. So we have 3/2 divided by negative 1/2, which gives us negative 3. For the second expression with x equals 1/2, we have 1/2 squared plus 1/2 in the numerator. 1/2 squared is 1/4, plus 1/2 gives us 3/4. In the denominator, we have 1/2 squared minus 1/2, which is 1/4 minus 1/2, giving us negative 1/4. So we have 3/4 divided by negative 1/4, which equals negative 3. Once again, both expressions give us the same value, -3 when x equals 1/2. Let's try one more value. Finally, let's evaluate both expressions when x equals -1. For the first expression with x equals -1, we have -1 plus 1 in the numerator, which is 0. In the denominator, we have -1 minus 1, which is -2. So we have 0 divided by -2, which equals 0. For the second expression with x equals -1, we have -1 squared plus -1 in the numerator. -1 squared is 1, plus -1 gives us 0. In the denominator, we have -1 squared minus -1, which is 1 plus 1, giving us 2. So we have 0 divided by 2, which equals 0. And again, we find both expressions equal 0 when x equals -1. Let's look more closely at these two expressions to understand why they give the same values. If we factor out x from both the numerator and denominator of the second expression, we get x times the quantity x plus 1 divided by x times the quantity x minus 1. The x terms cancel out, and we're left with exactly the first expression. This is why both expressions produce the same result for any value of x except 0 and 1, which make the expressions undefined. In conclusion, we verified that the expressions x plus 1 divided by x minus 1 and x squared plus x divided by x squared minus x are equivalent for all values where they're defined. This equivalence is because the second expression can be simplified to the first by factoring and canceling the common factor x. This is a good reminder of how algebraic manipulation can reveal the true nature of expressions. We have the function f of x equals 2x minus 1, and we need to evaluate it at x equals 5. To evaluate this function, we'll substitute x equals 5 into the function expression. So we write f of 5. Next, we substitute x equals 5 into the original function expression. So we have 2 times 5 minus 1. Now, we multiply 2 and 5 to get 10. Finally, we subtract 1 from 10, giving us 9. So f of 5 equals 9. Let's visualize what we just did. We have a function machine that takes an input value, applies some operations to it, and produces an output value. In this case, our function is f of x equals 2x minus 1. We input the value 5, and the function multiplies it by 2, and then subtracts 1. The output is 9. Let's move on to our second example. Here we have the function f of x equals x squared minus 1, and we need to evaluate it at x equals 3. Again, we'll start by writing f of 3. Next, we substitute x equals 3 into the original function expression. So we have 3 squared minus 1. 3 squared is 9. Finally, we subtract 1 from 9, giving us 8. So f of 3 equals 8. We have a function f of x equals the quantity x squared minus 2x plus 1 raised to the power of 17. We need to evaluate this function at x equals 1. Let's start by writing what we're solving for. We want to find f of 1, which means we need to substitute x equals 1 into our function. Next, we'll substitute x equals 1 into our function. We get f of 1 equals the quantity 1 squared minus 2 times 1 plus 1, all raised to the power of 17. Now, let's simplify the expression inside the brackets. 1 squared is 1, minus 2 times 1 is minus 2, plus 1 gives us 0. So we have 1 minus 2 plus 1 equals 0. Continuing with our simplification, we get 1 minus 2 plus 1, which equals 0. So our expression becomes 0 raised to the power of 17. Finally, 0 raised to any positive power is still 0. So f of 1 equals 0. Let's look at a more complex example. We have a function f of x equals the product of x plus y plus c, and the quantity xy plus yz plus xz minus xyz. We need to evaluate this when x equals negative y. First, let's identify what we're solving for. We want to find f of negative y, which means we need to substitute x equals negative y into our function. Let's substitute x equals negative y into our function. We get f of negative y equals the quantity negative y plus c times the quantity negative y times c plus negative y times z minus negative y times c. Now, let's simplify step by step. In the first bracket, negative y plus y equals 0, so we're left with just z. In the second bracket, negative y times y equals negative y squared. Then we have y times z, which is yz, and negative y times z, which is negative yz. So the second bracket becomes negative y squared plus yz minus yz, which simplifies to just negative y squared. For the last term, negative y times y is negative y squared, and then multiplied by z gives us negative y squared z. Continuing with our simplification, we have z times negative y squared, which is negative y squared z minus negative y squared z. This gives us negative y squared z plus y squared z, which equals 0. Finally, negative y squared z plus y squared z equals 0. So f of negative y equals 0. In conclusion, function substitution involves replacing variables with specific values and then simplifying the resulting expression. We've seen two examples where we substituted values and found that both functions evaluated to 0. Remember to carefully substitute the values, then simplify step by step using the appropriate algebraic rules. We're given the function f of x equals x to the fourth power plus x squared plus 1. And we need to find the value of this function when x equals the square root of 2. To evaluate this function, we'll substitute the value of x, which is square root of 2, into our function. So we get f of square root of 2 equals the square root of 2 to the fourth power plus the square root of 2 squared, plus 1. Now, let's simplify this expression step by step. First, let's simplify the square root of 2 to the fourth power. We know that the square root of 2 squared equals 2, so the square root of 2 to the fourth power equals 2 squared, which equals 4. Let's simplify this expression. We know that the square root of 2 squared equals 2, so we have 2 squared plus 2 plus 1. Now, we calculate 2 squared, which equals 4. So we have 4 plus 2 plus 1. Finally, we add all these numbers. 4 plus 2 equals 6, and 6 plus 1 equals 7. Therefore, f of square root of 2 equals 7. Let's move to our second example. Here, we have a function f of a and b that equals the quantity a plus b, all cubed. We need to evaluate this function at the point where it equals 2 and b equals negative 3. To evaluate this function, we'll substitute the values of a and b into our function. So we get f of 2 and negative 3 equals the quantity 2 plus negative 3, all cubed. Now, let's simplify inside the parentheses. 2 plus negative 3 equals negative 1. So we have negative 1 cubed. Finally, negative 1 cubed equals negative 1. So f of 2 and negative 3 equals negative 1. In summary, to evaluate a function at a specific value, first, identify the function and the value at which you need to evaluate it. Second, substitute the given value into the function. Finally, simplify the expression step by step to get the final answer. Now it's your turn. Try evaluating these functions on your own. F of x equals x squared minus 3x, when x equals 4g of a, b equals a squared minus b squared, when it equals 3, and b equals 2. Pause the video to solve these. And remember to follow the step-by-step substitution method we've demonstrated. We have the function f of a, b equals a cubed plus 3, a squared b plus 3, a b squared plus b cubed. And we need to evaluate this function at the point where it equals 2 and b equals negative 3. First, let's substitute the values of a equals 2 and b equals negative 3 into our function. We'll replace every a with 2 and every b with negative 3. Now, let's calculate each term individually. First, we calculate 2 cubed, which is 2 times 2 times 2, giving us 8. Next, we have 3 times 2 squared times negative 3. 2 squared is 4, so we have 3 times 4 times negative 3, which is negative 36. For the third term, we have 3 times 2 times negative 3 squared. Negative 3 squared gives us 9, so we have 3 times 2 times 9, which equals 54. Finally, we have negative 3 cubed, which is negative 3 times negative 3 times negative 3, giving us negative 27. Now, let's put all the terms together. We have 8 plus negative 36 plus 54 plus negative 27. To make this easier to calculate, let's group the positive and negative terms separately. We have 8 plus 54, which equals 62, and negative 36 plus negative 27, which equals negative 63. So our final calculation is 62 plus negative 63, which equals negative 1. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.